Hello and welcome to Numeristical. It's been a while since I've created some content, but I am back and I'm going to be letting out a series of videos, hopefully pretty consistently going forward for a little while at least. This next set of content that I'm going to bring to you is more general in nature. So we're really going to talk about data science and machine learning uh, in a sort of a big picture basis and focusing on gradient boosting and how you can use gradient boosting in a variety of ways. This first set of videos is a short course that's about data science and machine learning in business. So it'll be most applicable for people who really want to know how to use machine learning in business, or perhaps you're already working in an industry job and you'd like to get an overview of the field. So with that said, before I go forward with the video, I'd like to ask you again if you could please like the video and subscribe to the channel. It would really help me out a lot. These next few videos, again, they're going to be about data science and machine learning for business. This first video is going to be an overview of kind of why you might build a model and going over the supervised learning framework and some terminology and so forth that will set the stage for the rest of the series. So I hope you enjoy it, and let's get right to it. So why would we build a model? And thinking about supervised learning in particular, well, the most common thing people come to when they think about building machine learning models is for the purpose of prediction and generally to build some sort of a data product. So something like fraud detection. Fraud detection, you have data about your past fraud and you want to learn how to classify transactions as being higher or lower risk for fraud. And the goal is so that when you see future transactions, you want to be able to automatically determine if they're fraudulent or not. Ad serving is a similar kind of problem. You have space on your website, you've got some information about the user who's loaded your web page, and you want to show them ads that they're likely to click on. Insurance risk assessment. There, the goal is you've got some information about the person who wants to buy a policy. Let's say it's an auto insurance policy. And you want to know what's their probability of getting into an accident, and perhaps also how expensive that accident is likely to be, so that you can set your premiums at an appropriate level. And loan default prediction. Again, you have some information about a potential borrower, and you want to understand how likely they are to pay back that loan so that you can decide whether to approve or deny that loan, and also perhaps what interest rate you should charge on that loan to cover your risk. In all these cases, the idea is that we need to make a decision repeatedly and automatically. All of these, probably in the past, were done somewhat manually by human review. And now the idea is we want to do it much more quickly, and we want to do it in a much more data-driven fashion. So there's two big advantages. One is that you can make it very quickly and handle many decisions in parallel. And the second is that it's ideally data-driven. It's not subject to human biases or emotions or miscalculations. Now, that's what I think most people think about when they think about building machine learning models, is prediction. But there's another reason to build a machine learning model, and it sometimes is in conjunction with building a product, but it also could be separate. And that's just analysis or inference. And the goal there is really just to understand the process that generates the data. So consider a problem like churn prediction. Churn refers to when you've got some sort of a subscription service and people unsubscribe, people leave, they stop wanting to pay for that service. And you might want to build a churn prediction model as a data product. You might want to say, I'm going to predict on all my customers, and if I see that somebody's at high risk for churn, I'm going to give them 1 month free, or I'm going to give them some incentive to stay on longer. However, you also might want to build that same churn prediction model purely just to understand your business. If you see that a certain demographic is churning at a higher rate, you might want to understand why that is, or what is not serving that customer well. Similarly, if you built a churn prediction model and found that a bad customer service experience was a high predictor of churn, that might tell you something about how to improve your business. Another problem might be disease onset. So again, suppose you have some medical data, you're working in the medical field, and you want to build a model for how likely people are to get a particular disease. Now, there might be a sort of data product reason to do this. You might want to run this model against all your patients and see who's most at risk of getting this disease and hopefully give some intervention that would help mitigate that. However, you also might want to build this model just to understand this disease, understand what organ systems are involved, understand whether social factors are playing a role, and so forth. Finally, suppose you built a model for house prices. Now, we've seen on real estate websites that this is a very useful data product when they show real estate. When they show houses on these websites, they'll often show an estimate of how much that house would cost to buy. But building this model could also help you understand the real estate market, could help you understand, for example, how much another bathroom would be worth in my house, and that could also be used to aid other kinds of decision making. Next, we're going to define and just go over the supervised learning framework. I want to define some of the notation and just some of the terminology so that everyone's on the same page as we discuss what it means to have a supervised learning problem. So what is our supervised learning framework going to look like? Well, first let's talk about our data. And we're going to think about our data as being organized into rows, where each row is a single instance or data point. And we've got a set of features, also called predictors, other terms for them. And these are organized into columns. So this data matrix, where the rows are the individual data points and the columns are the different features of each data point, is represented by a capital X. And they use a capital X traditionally because it's a matrix and it has multiple columns. Now, conversely, you also have a target, Y, which is the outcome or the label of each of those data points. And we usually use a lowercase y to represent sort of those answers. And this is used because the y is typically a single column. There's usually one answer that you have for each data point in your supervised learning framework. And we think of our data as having observations, and each observation is a pair xi, yi. Xi being the features, the predictors, and yi being the answer, the thing we're trying to predict. So the classical assumption of supervised learning is that there's some data generating process which produces the pair xi, yi. And this is often called a joint distribution. There's some process which you can think about as rolling a bunch of dice or spinning a bunch of wheels to generate some randomness. But at the end of that process, you get a pair xi, yi. Now I think it's often more useful to think about this process as it generates an xi and then it generates a yi given the xi. Now mathematically those notions are equivalent, but it's, I think, a little bit easier to think about if you think about it generates an xi and then it generates the yi given the xi. Because at the end of the day, the supervised learning process is really about just learning that second part. You're really trying to learn what's the probability distribution or some other representation of the uncertainty of yi given xi. Now, the fundamental mathematical assumption behind the supervised learning framework is that this data generating process stays the same. Now, what do we mean that it stays the same? We don't mean that it gives the same outcomes every time, but we mean that it's the same process every time. So to put it in terms of dice rolls, we're not saying you're going to get the same outcome every time you roll the dice. What we're saying is the dice are staying the same. We're not weighting the dice in between rolls. We're not going to use a different set of dice with a different set of probabilities next year that we're going to use this year. So that process stays the same. And mathematically, they refer to this property as being stationary. That this probability distribution, this data generating mechanism, is the same random generating mechanism all the way through our training set, our test set, and in the future instances in which we plan to use it. Now in practice, this is frequently untrue. And you can think of any number of examples to show this. I've worked on some problems predicting baseball games. And baseball, even though it's the same rules in the same game, mostly, they do change the rules from time to time, or the way that the strategies of the game change, so that it's not necessarily a stationary process. So whenever you're working on real world problems, you have to add on some common sense to the theory. You have to realize that these fundamental assumptions are assuming that the data process is the same all the way through, and when you know that it's not, you sometimes have to think about, well, how can I adjust what I'm doing to accommodate the fact that I know this assumption is not going to be true in practice. Now, in supervised learning, there's typically broken up into two different kinds of problems, classification and regression. So if the target, Y, is categorical, we refer to the problem as classification. And the most common kind of classification is where it's just two possibilities. We'll think of them as yes and no. This is called binary classification. And this is a very, very common form of classification problem. If you're doing a classification problem and there's more than two different possible values of the target, and it's still categorical, you call that multi-class classification. And if the target is numerical, so it's a number, and typically you think about it as being continuous, or maybe it's integers, but the idea being that the different values kind of have that structure where they're next to each other, then we think about that problem as being, we call that problem a regression problem. Now, in supervised learning, the goal is to predict the Y value given the X value. But what do we mean by predict? And we'll see that this is actually a very difficult question to answer, and it's very nuanced, and it can mean many different things. So next, let's talk about the different types of predictions you might make in a classification problem. So what are these different types of predictions? Well, the first kind of prediction you might think about is what I would call a hard prediction. So you're given the xi, you're given your predictors, and you want to choose a single possible value of y as your prediction. So for example, the image classification, you're given xi. Xi is a set of pixels that make up the image, and you have to say this is a cat or this is a dog. Now, in binary classification, there's also this notion of a ranking prediction. So what this means is we're going to give a score to y based on the x that says how likely you are to be yes. And the idea is that this doesn't necessarily need to map to a probability. So for example, if you're doing fraud detection, you could think about a risk score where you give some number, and the higher that number is, the more likely it is to be fraud. And you might act on this by saying, okay, I'm going to pick a threshold, and if it's above this threshold, I'm going to take some certain action on this case. So again, you're not making a hard prediction. You're not saying this is fraud, this is not fraud. You're saying here's a score, and a higher score means I'm more likely to be fraud. And then a third kind of prediction is probability prediction. So this is given your x, given the predictors, you want to assign a probability to each of the possible values of y. So this is, I would say, the most kind of the most sophisticated kind of prediction. Now, why is it the most sophisticated? Well, if you think about it, if I've got a probability prediction, I can easily make a ranking prediction out of it, right? I just rank the cases from highest probability to lowest probability. And if I have a ranking prediction, I can easily get a hard prediction from it. I just choose some threshold and I declare everything above that threshold to be yes and everything below that threshold to be no. So you can easily move from sort of the bottom of the slide to the top of the slide. You can go up very easily. But going down, it's not quite so easy. If I have a set of hard predictions, I kind of lose the information about ranking within each of those classes. Now, what are some examples of classification predictions? Well, let's say I'm working in loan default prediction. A hard prediction would mean that for each loan application, for each borrower, I'm going to predict yes or no whether they default or not, whether I think they're going to default or not. In a ranking prediction, I would give a risk score to each borrower, where higher score means they're more likely to default on the loan. So this would be just like a credit score. Now, credit scores, higher numbers mean you're less likely to default on a loan, but it's the same concept. The score doesn't necessarily translate into a probability, but we know that a higher score means more likely for a particular outcome in the binary classification problem. Finally, I could also frame this as a probability prediction problem, where I want to assign a probability of default to each borrower. So for example, I might say, this particular borrower, given all their information on their loan application, is going to default with probability 12%. Now let's take another classification problem. Let's go back to this image classification. So if I'm doing hard prediction, this might say, just predict what the object is in the image. So I might say, this is a picture of a cat. This is a picture of a maple tree. This is a picture of a skyscraper. You could also frame this, however, as a probability prediction problem, where you assign a probability to every possible object type, and where those probabilities sum to 1. So you could say, in this image, with probability 99%, this is a cat. There's a 0.9% probability that this is a hamster. And then you've got this very small fraction of a percent for all of the other possible object types. Now, in a less certain case, you might say, here's a picture of a tree. I'm 70% sure this is a maple tree, 29% chance that it's an oak tree, and again, some very small fractional probability for all the other classes, so that they sum up to 1. So the word predict is complicated. Are we saying, when we say I want to predict Y, are we saying we want to give an answer, yes or no, or exactly what the answer is? Or are we trying to give something more nuanced and something softer? So in the previous two problems, we had the loan default prediction and the image classification. Which one do you think it makes more sense to think of in terms of hard predictions? So I would argue that the image classification problem is more amenable to hard predictions. And now, why is that? Well, when we're doing image classification, it's reasonable to expect the probability of one of the classes to be close to 1 and the probabilities of the other classes to be close to 0. Because we know there's enough information in that image, for the most part, to tell us what it is. If we see a picture of a cat, we know there's enough information to tell that this is a cat. So we have enough information to have high certainty about what the true answer is. By contrast, the loan default problem, it's not reasonable to know exactly who's going to default and who will not. You don't look at loan applications and say, this person 100% sure they're going to default on the loan, and this person I'm 100% sure they're going to pay it back. This takes us to the notion of high signal versus low signal problems. And this is an important concept to have in the back of your head when you're thinking about your business problems to think about what domain am I in and how should I approach the problem. So what's the difference between a high signal and a low signal problem? Well, in a high signal problem, there's enough information in X to achieve near certainty in Y given X. So again, in the image, we know there's enough information to determine for sure if this is a cat or a dog, because I look at it and I know if it's a cat or a dog. So if our model, assuming their model is using all of the available information as well as it could be used, we would expect those predicted probabilities to be very close to 0 or 1 for the different classes. We expect one class to have probability close to 1, and all the other classes to have very low probability. And so in high signal problems, it makes sense to think in terms of hard predictions, because we're usually not interested in assessing the degree of certainty. We're usually just more interested in assessing it in terms of right and wrong. Now in a low signal problem, we've got sort of the opposite set of things going on. So there's not enough information in X to achieve near certainty in Y given X. When I look at that default prediction problem, there's just not going to be enough information there for me to say I'm 99.9% sure this person is going to pay their loan or is not going to pay back their loan. And so we don't expect the predicted probabilities to be close to 0 or 1. In loan defaults, you typically have a situation where, maybe your safest borrowers would be less than 1% default risk, but even your riskiest borrowers would maybe be 20 or 30% default risk. It's rare to see a case where you would say, 70%, 80%, 90%, this person is going to default on their loan. In fact, you just probably wouldn't give them a loan to begin with in that problem. So often in imbalanced problems like loan default prediction, the probability of the rare class will always or almost always be less than 1/2. And we'll see why this is important, why I'm calling this out, is because if you're forced to make a hard prediction, it's going to be kind of boring. If you're forced to make a hard prediction on the loan default problem, you'll say, every person, I'd say they're more likely to pay it back than not, so I'm just going to guess that everyone's going to pay back their loan. So, and we'll dive deeper to that a little bit later on. But the moral of the story here is that in low signal problems, you should think in terms of probabilistic predictions or ranking predictions. But hard predictions are not the right framework in which to evaluate an algorithm or in which to approach the problem. You shouldn't be thinking about in terms of right and wrong if you don't have enough signal where it's reasonable to make a right or wrong prediction. Next, let's talk about the different kinds of predictions one might make in a regression problem. Now in regression, the discussion has been very, very dominated by what I'll call point prediction, which is given your xi's, choose one numerical value as their prediction of yi. And most people take this as given as what else could it be? I'm trying to predict y, I should just guess a number and see how close my number is to the true y. But there are other ways you could think about making predictions in a regression problem. So another thing you could do is make an interval prediction. So given those same set of predictors, give an interval AB such that your yi is likely to be between A and B. And typically this would come with a coverage value. You would say how likely it is that your interval covers the true value, with what probability. So for example, you might say, given this xi, yi is going to be between 5 and 10 with probability 0.75. Another nuance here is that rather than an interval, it might be a region. You might actually have a set of intervals. And it may not be obvious at first why you would ever have a set of intervals rather than a single interval. But we'll see later if you've got a prediction where there's a bimodal distribution, then it might make sense to say, I'm either going to be in this interval or in this interval. The final kind of prediction we want to talk about is framing the problem as probabilistic regression, which is given your x, you want to give a full probability density on y given x. And we're going to show a little later what that might look like. But this is also what's called, in classical statistics, this is called conditional density estimation. So you really want to understand what's the shape of the density, which values are more or less likely, and get some sense of the proportionality between those different outcomes. Okay, so let's frame this with some examples. So let's say my regression problem is house price prediction. I want to predict the sales price of a house. So a point prediction would say I'm going to predict a single number, $300,000. I think this house is going to sell for $300,000. An interval prediction might give a little bit more of a sense of your uncertainty around that number. So you might say, well, I'm 80% sure it's going to be between 280,000 and 350,000. Now, a region prediction would be similar to that interval prediction, but suppose you want to consider two not connected intervals. So you might say with 80% probability, it's going to be either between 270 and 290 or between 320 and 350. So maybe for some reason you think there's some bimodality that, if you get good weather at your open house, it'll go for this higher range. And if you get bad weather during your open house, it'll be in this lower range. And finally, for probability prediction, you would output a full probability density over all the possible prices of the house. So let's see some pictures of what these look like, and I'm going to do them in terms of another problem, which is predicting the strength of concrete. So this is a data set that's on the UC Irvine repository, and it's a scientific problem where you are trying to predict the strength of the concrete given some attributes about the recipe. So you put in some cement and some rocks, and you let it sit for a certain number of days, and based on that, you're trying to predict how strong this concrete is going to be. And so here we see 4 pictures which represent the 4 different kinds of predictions one might make in this problem. In the upper left, we see point prediction. Well, that's just, I'm going to put a vertical line and say, here's what I think the answer is going to be. In the bottom left, we see an interval, and you might have a coverage value, let's say 80%. And so in this case, you're saying, I'm 80% confident that the true answer is going to be between these 2 endpoints. In the bottom right, we see a region prediction. So there we see, it's similar to the interval prediction, but I've got 2 different intervals that aren't connected, and I'm saying I'm 80% sure it's going to be in one of those 2 intervals. And finally, in the upper right, we see a distribution prediction. And here you see that we have a bimodal distribution, one very, very strong mode around, let's say 50, 55, and then a smaller mode around 40. And just to say a little bit about how distribution predictions relate to these other predictions. So given the distribution prediction, you can get an interval prediction or a region prediction. Now the interval prediction, typically you would get by taking the center of the distribution. So since that distribution shows me 100% of the possibilities, if I want an 80% confidence interval, or prediction interval I should say, if you wanted an 80% interval, you would chop off the 10% on the left and right, and you'd get the center 80%. You'd say I'm 80% confident I'm going to be in this range. Now, a region prediction, you'll see, why would you have discontinuous intervals? Well, it turns out that because this distribution prediction is bimodal, if you want the narrowest, kind of the smallest set that contains 80% of the probability, you actually want to have 2 different intervals, each around the 2 main modes there. So it turns out that those both the interval prediction and the region prediction have 80% coverage, but the region, if you add up those 2 intervals, it's actually smaller than the interval in the interval prediction. And finally, the point prediction is the simplest. And if you were given the distribution in the upper right, and you want to make a point prediction, there are different ways you could do it. You could say, I'll take the mean. You could say, I'll take the median. Or you could, if you had reason to, choose some other answer, some other function of that distribution. Okay, hope you enjoyed that video. The next video, we're going to talk about the metrics used for classification. We're really going to try to go into some detail and explain the different metrics and when you might want to use different ones and what they mean. And after that, we'll have another video about the metrics for regression. So those will be the next two videos. So I hope you'll join me for those. In the meantime, again, if you could like the video and subscribe to the channel, that would really help me out. And have a great day.